So last time, we made a tremendous amount of progress. We reviewed the time-dependent Schrödinger equation, and then we viewed some computer-generated solutions to that equation where we were exposed to a number of different phenomena that then will become the basis for our studies moving forward. In particular, we looked at traveling wave packets and saw how they spread in time, following our expectations previously from the Heisenberg uncertainty principle. We saw this very interesting phenomena of a wave packet hitting a potential step, which then generated a reflection and a transmission of probability. We also saw these very interesting states, these stationary states. We saw them actually in the example of the simple harmonic oscillator, although they exist for any potential. And the interesting thing about these stationary states is that the probability distribution just doesn't change in time at all. And there's a whole variety of different shapes to these, and these are very important states. We will learn more about them later on. We also saw a very cute example of so-called coherent states of the simple harmonic oscillator. This was where we took the harmonic oscillator's simple stationary state, which is a simple Gaussian type function. We pulled it back from the center of the oscillator and then let it go, and it simply kept its shape rigidly but moved back and forth following perfect simple harmonic motion. So from these movies and the phenomena we saw, they raised a very important question, though, which relates to how probability changes and flows through time. Because we had better hope that as we solve the time-dependent Schrödinger equation, somehow the equation is magically set up so that the probability that we see, the total integral under those probability densities that we saw, has to stay 1, because the probability of finding the particle somewhere at any point in time must add up to 1. And the way we decided to address that, because we clearly saw how probability was flowing, is through the standard mathematics of describing the conserved quantity which is flowing. This is something called the general continuity equation. So we wrote it down in its general form. You remember the various terms that enter in. You have the density of your conserved quantity, and you're looking at its time derivative, how it changes in time. For our particular case, that is a density per unit length, as all densities are, but it's a probability density because we're concerned with the conservation of probability. And that probability density we already knew was given exactly by the square of our wave function. Now, if the quantity is conserved so that the only way things can enter a given region is either through flowing in or us pumping them in or sucking them out externally, then the equation that follows is that the time derivative of this density plus the spatial derivative of the flow of that density measured as a current, in this case a probability current that measures the flow of probability past a given point x at any time t. And this is then a current, so it's measured as probability passing that point per unit time, had a particular mathematical form, which we proved generated something which then followed the general continuity equation. The sum of those two, if the quantity is actually conserved, then is the source or sink of that quantity in our system. Now, our result then for the probability current had a particular formula that we just saw. Our result for the source and sink had a very interesting result, namely that the source and sink is 0. That means that probability is only flowing through our system, that it's conserved, and that there's nowhere where we're pumping in or sucking probability out. The total probability has to stay 1. So the fact that we got this equation with a 0 on the right-hand side proves then this key result that the time-dependent Schrödinger equation does indeed conserve the probability. The final key aspect of this result is that we now finally have an explicit formula that tells us the rate at which probability is flowing through our system at any particular time t. And as you will see in the exercises, that's a very handy quantity to know how to calculate. And you will also see that it becomes very handy in some of our future developments. For instance, when we study this phenomena of reflection and transmission at a potential step. Great, so those were the key results from last time. Today we have something very exciting, because today we're going to continue with these general considerations, and we're actually going to prove the famous Newton's equation, F equals ma. This is so exciting because in all of our past physics courses, even your very first course in physics. You were told this Newton's equation, but you were never really told where it came from. You were just told that, well, that's just how the universe is. This summarizes all of our observations. But finally now we can actually prove this as a theorem based on a more fundamental underlying theory, namely this formal quantum theory that we've been building up.